Day 135, Honors Physics, Electrostatic Capacitors, Extra Practice Problem number 1. I'll put a number 1 up here. So I've filled in some values for these capacitors and the battery. The battery is 100 volt potential difference. Once again, one of the issues that will come with practice is figuring out where the parallel and series portions of this network is. And I can see this up to the top, that this 8 microfarad C sub 3 and C sub 4 is in parallel with the C sub 4, the 4 microfarad. Because once again, if I'm taking a walk around this circuit, if I start the battery, the positive side, and come around this way, and decide to go up here, once I get to this spot, I have two choices. Whenever you have two choices, you know something's in parallel going forward. This one and this one are in parallel because they come back together over here along this wire, because it's all one connection there. It's one wire, it's considered one spot. So the C sub 3 and the C sub 4 are in parallel. So the first step is to combine them, and the rules for parallel capacitors in series is to simply add them, 8 plus 4. So the new diagram will look like this. The 8 plus the 4 is 12. So I've replaced the 8 and 4, put them together as one capacitor, its equivalent capacitance of 12. The 5 and the 18 I've left alone. Now the 12 and the 18 are in series. If I go on that branch, up this branch, those are in a row right here. These two are here in a row. They are in series. So you do the rule 1 over 12 plus 1 over 18 equals 1 over C total. I'll do that. So the combined 12 and 18 equivalent capacitance is 7.2 microfarads. And I've drawn the new diagram, gotten rid of those two and replaced it with the 7.2. And now we have a 5 and a 7.2 that are in parallel. And that's just an arithmetic addition. 7 plus 5 is 12.2. So that'll be my last diagram. I'll draw that. And there we have it. That's your goal every time, is to get down to one capacitor. So I have 12.2 microfarads as the equivalent capacitance. Now if you have a problem like this and I ask you to find all the charges and potential differences for other capacitors, you have more work to do. You will be using this equation about 5 or 6 times. That is the equation C equals Q over V. Technically Q over delta V, but we get a little bit lax here with the delta V. It's the potential difference, which is the assumption all the way through here. Bottom line, you start with this last diagram. The capacitance is 12.2 microfarads, so you plug that in. 12.2 micro equals Q over 100. So Q comes out to be basically, well, 12.2 micro, which is 10 to the negative 6th, it comes out to be 12.2 times 10 to the negative 4th instead of negative 6 when I multiply by 100. So negative 4th coulombs. That's how much charge is stored on this equivalent capacitor. I'll write that down over here. It's 12.2 times 10 to the negative 4th instead of 6th coulombs. All right? Now, you start working yourself backwards and you pull information from each diagram to the next diagram up. So what's true in parallel is all capacitors have the same potential difference. These are each 100 volts. They're both directly connected to the battery's potential difference. So they're each 100 volt potential difference. And I'm going to plug into that blue equation once again. This equation over here, I'll circle it in blue. I'm just plugging in there every time. I'm going to plug in now for each of those individual capacitors. For the farthest left, the 5 micros, so I'm going to plug in 5 micros here and 100 volt here, and I'm going to get 5 times 10 to the negative 4th coulombs for that one. Write that down. Boy, negative 4. Wow, my pen. And the other one comes out to be 7.2 times 10 to the negative 4th coulombs. And you can add those two up. 7.2 plus 5.0 is 12.2 times 10 to the negative 4th coulombs. Total charge shared between those two, but on its equivalent capacitance, that's what it comes out to be. That's your check right there. Now you keep going backwards. the 5 microfarad capacitor is done. This guy's done. But these two guys are in series. They have the same charge as each other. And how do you know how much charge they have? Well, they have the same charge as their equivalent capacitance, the 7.2. So that's what you label up there. You label 7.2 times 10 to the negative fourth coulombs. That's negative fourth coulombs. And this is 7.2 times 10 to the negative fourth coulombs. So we know what their charge is on those capacitors. So you're going to once again come over here with this equation. We know the charge is 7.2 times 10 to the negative fourth. And we know the capacitance. You're going to calculate the delta V for each of those, the potential difference, which will not be 100. It'll add up to 100. So you don't need to show the work for this, but I've plugged into that equation, C equals Q over V, for each of those two capacitors, the 12 and the 18. And this top one came out to be 60 volts, potential difference. And the bottom one here, the 18 microfarad, came out to be 40 volts. Potential difference in 60 plus 40 is 100. So now my 18 microfarad capacitor is all solved. My 5 microfarad capacitor is all solved, but all I have left is the 8 and the 4. They're up here. Alright, they're in parallel. Their replacement is the 12. So I use some of the information from the replacement, the equivalent capacitance of 12. What do I carry back to the two capacitors? Well, in parallel, they both have the same potential difference. So you carry back this number here, the 60 volts. So each of these is 60 volts. That's the number that carries from the next diagram. Alright, so what I don't know for each of those now is the charge stored on each of them. So I'm going to go back to this equation once more, and you don't have to show the work, but write down the answers. I'm going to plug into this. I know C for each of the capacitors. I know delta V. Basically, you'll end up multiplying, and you'll get the charge stored. And that comes out to be 4.8 times 10 to the negative fourth coulombs for this capacitor, and 2.4 times 10 to the negative fourth coulombs for this capacitor. Once again, if you add up those two numbers, that charge, total charge stored on those two capacitors there, you get the total charge stored on its replacement capacitor. We've basically finished the problem. It could also ask you to figure out how much energy is stored in each individual capacitor, or it could ask you to find the energy stored in the overall capacitor down here. And a check would be, if you calculated the energy stored down here using the equation for energy stored, or potential energy, U equals 1/2 QV. You could figure out the total energy stored in that last capacitor, and then you could check it by adding up all the energy stored in all 5 of these up here, all 4, I'm sorry. You take those 4, figure out how much energy is stored in each one individually, add them all up together, each one will be in joules, but the total energy stored in these 4 should add up to the total energy that would be stored in this one down here. And you can check that. I'm not going to do that right now, but that'd be something you could check if you wanted to. Some of the other teachers or books will give you more equations than just this equation over here for energy stored. Because, for example, I can plug this value, Q over V, technically delta V, well actually, solve it for Q. Solve this equation right here for Q, and Q is equal to C delta V. So if I take C delta V, I can plug it in over here for Q, and basically mixing those two equations together gives me a new equation for energy stored. That is U equals 1/2 CV squared. Once again, it's always delta V, but you'll see that in a lot of books, that the energy stored in the capacitor is 1/2 CV squared. It's just combining that blue equation on the left, this equation here, plugging in for Q, because Q is going to be C times V. And you can come up with other equations as you mix and match, but those are the two most popular equations you'll see for the energy stored in a capacitor.
Mr. Rink, you work too hard.
What's that?
You work too hard.
Everybody works too hard.
I told Rachel the other day, I was like, Rachel, tell your dad how much we appreciate him and how hard he works. And I was like,
nice.
I unfortunately don't think I appreciate physics as much as Mr. Rink does, but I do appreciate the amount of work that you spend for the people who do love physics. And I mean, yeah, oh my goodness, Mr. Rink.
A lot of it I like. There's some parts of it I don't like. I mean, nobody likes working long hours, but I mean, I'm making these videos right now, but I don't mind making them. It's just the fact that I'm making them at 7 o'clock at night or whatever it is, honestly. But whatever. But, what do you guys got, soccer right now or what?
I had soccer and then pit orchestra.
Yeah,
so.
okay, well, see, you guys are sort of the same boat.
Yeah, well,
But thank you.
Yeah. Well, you're appreciated, Mr.
All right,
Rink.
thank you.
Even if I didn't appreciate physics,
Well,
I
you know,
appreciate
You do so hot in your class. You're still
You guys did okay.
Okay.
So,
I survived.
all right.
It was art.
Have a good night.
Hmm.